All right, so it's a pleasure today to have Dr. Steve DiMarco from Texas A&M University as our seminar speaker. He has several titles here, as you can see. He's a Bill Bryant or William Bryant Chair of Oceanography, Teaching, Research, and Mentoring Excellence. He's a professor in the Department of Oceanography, Department of Ocean Engineering, and he's the director of the Geochemical and Environmental Research Group, all at Texas A&M, and quite impressive. Dr. DiMarco's research is focused on using ocean observing systems, and he's applied his expertise in ocean observing in a wide range of environments from the Gulf of Mexico into global areas. But what he's going to talk about today is some work that has been done in the Gulf of Mexico. He is one of the PIs on a large National Academies of Science funded research looking at understanding and predicting the loop current going in the oceanography or the circulation of the oceanography of the Gulf of Mexico. And he's going to talk about an experiment done in the Yucatan Channel in 2004 as part of that project. And he's also going to talk about freshwater fate from Hurricane Harvey, which is really very relevant to the recent hurricanes we've had from Helene and Milton. So I'm going to turn it over to Dr. DiMarco here so he can talk about the observing system case studies. So please go ahead.
Great. Thanks, Eileen, and thanks everyone that's listening today and tuning into the talk. I'm really happy to be here, and I really appreciate the invitation. So I'm going to talk about these two things that are related to ocean observing. So the Yucatan Channel MASTR experiment and the Hurricane Harvey stuff. And the order that I'm going to talk to you, so I'm going to say a couple words about GERG, the Geochemical Environmental Research Group. And then the second part will be what happened to 162 cubic kilometers of rainfall that fell during Harvey on the Texas coast and on the Texas coastal water. And then something that's very new just happened earlier this year, talk about the mini adaptive sampling test run experiment. So we call it MASTR, which is part of the National Academy Gulf Research Program, Understanding Gulf Ocean Systems program. And again, in 2024, this was in the Yucatan Channel. So some of the things that we found out about that. Some words about GERG. So good words about GERG. So GERG is so for those that have been here before, and some of you have, the map is up there on the upper right of your screen, and we're about 5 miles south of the main campus, and so we're off campus. There's about 25 full-time employees here. The center itself was established by James Brooks, as a graduate student, and that was in the late 1970s, and it became a center of excellence. And those that have administrative experience on this call know what that kind of thing designation means. The last line there, though, it says that it is soft money. GERG is 100% soft money, which means for those not initiated with soft money or hard money, it means that we have to find all the funds to operate GERG need to be found through extramural grants. So we eat what we kill, as we say. Also, the ocean observing business at GERG accounts for about 80% of our budget, annual budget, and so I'm going to focus on that. The other about 20% is the chemistry part, geochemistry, environmental chemistry. I'm not going to really talk about that. I'm going to focus on the ocean observing side. So we respond to national, state, and global type needs for ocean observations and focusing on the near real-time aspect and to inform numerical prediction and to provide decision makers and first responders information that they can use in a near real-time way. So one of our principal funders here is the Texas General Land Office, which has the purview for oil spill response and mitigation. And they've been funding for 30 years our buoy program. Also, we get significant funding from NOAA for glider work, basic science, and also for high frequency radar. And we also have portfolio. So with a soft money institute, you make sure you have a portfolio that is pretty diverse. So we have funding streams with the National Academy, NOAA, National Science Foundation, Department of Energy, the Navy, the state of Texas, and also private foundations and with industry. This is showing the Texas Automated Buoy System and the family of buoys that are constructed, designed, engineered for that system are done right here at GERG. So that's what that inset at the upper right shows. The Texas Automated Buoy System real-time website is there, given by tabs.gerg.tamu.edu. You can find the live data right there. And again, I said it was funded by the Texas General Land Office. It's been in continuous operation since April of 1995. So we're about 30 years into the continuous observations of that system. And there's 10 coastal and bay buoys associated with this, reporting in real time. And there's also an additional 2, which were just continued a couple years ago at the Flower Garden Banks National Marine Sanctuary, which is about 125 miles offshore of coastal Texas. And you can see my cursor, Flower Garden Banks is down about here. So that's at the shelf break. They were discontinued around 2018, but we would like to put them back. They do measure real-time surface currents, temperature, salinity. So there's a CTD on that also get atmospheric variables, and there's fluorometers that give us some of the hydrocarbon variables as well. But again, the primary mission for the Texas Automated Buoy System is oil spill response and mitigation. So we go to the next one. So we also have autonomous vehicles, and this is just a slide showing that we have Slocum gliders. We've had them since 2012. We have about 60 some missions in that time period, which makes us a medium-sized operator. We also have surface vehicles like the liquid robotics wave glider, and that particular vehicle will make its way into this talk today. And also we have one Autonaut, which is made in the UK. Next slide. High frequency radar. We operate 6 locations on the Texas coast. They start up here in the upper East Coast at Rollover Pass, which is near the Louisiana-Texas border, and they go all the way down to Port Mansfield, which is near the King Ranch. Down here at South Padre Island, almost to Brownsville. And so they cover the coast of Texas essentially from the Mexican border all the way to the Louisiana border. We also operate as part of the UGOS project under the National Academy. We operate 2 sites. We do this in conjunction with UNAM, the National Mexican University, and with Rutgers. And so this map over here shows the footprint for the 2 radar we have at Isla Cantoy, which is the north site, and Puerto Morelos, which is the south site here. Looking towards the east, when I get to the MASTR program, I'll talk to you a little bit more about that. So let's talk about Harvey. So Harvey made its landfall near Rockport, Texas. So in this location here. This is on August 25th, 2017. It came in as a Cat 4. The thing about Harvey's that came in, it made the landfall. Let's see. So let me play this animation. Is that it made 2 landfalls. It came in near Rockport, and that's just north and east of Corpus Christi, Texas. It spun for a day near Victoria, Texas, and then came back out into the coastal ocean before passing along the north and east along the Texas coast, and then made a second landfall near Cameron, Louisiana, before going up into the north to the northeast. The left animation showed some precipitation. The right animation shows the sea surface temperature anomaly and some of the cold wake that the storm left behind. So there was lots of human suffering that occurred during this storm. There was loss of life. There was lots of damage to property. This upper left graphic shows west. So the picture here shows West Houston flooding. That's where the flooding was most severe in the city of Houston. The graphic in the lower part of the screen, more than 500,000 cars were destroyed during this storm in the Houston area. All those cars had to go somewhere, and that picture here shows the speedway that's very close to Texas A&M. So we're 120 miles from the coast and 80 miles from Houston. All those cars had to go somewhere, so they put them at the raceway, and there they sat for several months. The graphic in the upper right is the interstate that connects Houston with New Orleans. It's the interstate that runs across most of the southern part of the United States, so I-10. This particular graphic, our picture, was taken near Winnie, Texas, which is about 70 miles east of Houston. And it's showing the highway there, I-10. And one thing to note about this graphic is that picture is taken 30 miles inshore. So what you're seeing there is not inundation from seawater onto land. This is rainwater that collected very close to this city called Winnie, 70 miles to the east of Houston, and has to make its way back out into the coastal ocean. So that is more than 6 feet of rainwater that's white capping on I-10 east of Houston. So to me, that was one of the most dramatic pictures that I saw throughout this whole ordeal of this storm. So how much rain fell? So we can go back into the observational record. So this is using the Global Precipitation Measurement Satellite Cluster, so the GPM, from NASA. And what the graphic is showing is the cumulative rainfall from the 23rd of August to the 1st of September 2017. So this covers both of the landfalls and the approach of the storm. And this is all gridded onto a 10 kilometer by 10 kilometer grid. And what it says here is that the total volume of rainfall that fell on land and on sea during this time period was this 162 cubic kilometers, or 39 cubic miles, or a 3.4 mile cube. So a lot of water fell on this area. And what I'm going to try to show you today is where did that rainfall go? What's the budget associated with that? So where did the rain go? That's the guiding question. We did get a National Science Foundation Rapid grant, and the director of GERG at the time, was Tony Knapp. Tony Knapp was director here about 10 years. And one thing Tony always told me is that if you're going to ask for a rapid, you better be fast. So they call them rapids for a reason. So as the storm was making its way in, we sent our proposal. It was on the desk of National Science Foundation within 48 hours of landfall. So we got in very, very early. And the two questions that we were posing is, where is all that rain going? And because the Flower Garden Banks National Marine Sanctuary, the coral reef off of Texas, is very susceptible to freshwater intrusions and could cause mass die-off. In fact, a year before, there was a mass die-off. We wanted to be able to track the freshwater plume as it came out. Came out through people's backyards, through people's houses, from their driveways and garages, across their yards, and into the coastal ocean. Slide here. So we were very fortunate because we had just done actually 2 cruises in the summer of 2017, one in June and one in August, where we performed this pattern of red stations here, and this was paid for by the NOAA Restore Act, which was the penalty phase and the recovery phase of the Deepwater Horizon spill. So after the fine was paid by BP and others, that funding or that money went into U.S. Treasury, and then it was doled out back to the Gulf of Mexico states and through the Restore program. And so we were doing some cruises to look at some of the new baseline for the hydrography along Texas. With the National Science Foundation money, we were able to do the September cruise and then a 4th cruise in November. The cruises are based around these 5 cross-shelf transects and transmitting all the way to the Flower Garden Banks, which is out here. Also shown in this graphic are where the tabs buoys are located. Those are the large capital letters. And so they provide time series, which allows us, if we are anchoring time with the hydrography cruises, the connectivity of the time series of the different moorings that are reporting in real time every hour from the tab buoys fills in the gap, the temporal gap between the spatially resolved hydrographic cruises. So, okay, let's go to the next here. So, what does this show? So this is bread and butter for the oceanographer in general, definitely for the physical oceanographer. But the bread and butter here is the TS plot showing the temperature and salinity from those 4 different cruises. I'll start with the green here, and this is just essentially showing the TS relationship. And remember, with temperature and salinity diagrams like this, temperature is a proxy for depth. So the lower temperatures are deeper and the higher temperatures are closer to the surface. What the green is showing here is that it's colder in November, and that shows that the fresher, colder water has this kind of structure, and that at these higher densities and higher, these dashed lines are isoplets of density here, with increasing density to the right. These values here, being on top of one another, show that not much variability in the deeper water on the shelf between early summer, June, and the middle of the fall in November. The big differences, though, are in the surface waters, and in September, that's the Hurricane Harvey that has the freshest signatures, and so you can see salinity is getting less than 15, bordering close to 10. In June, this is when there's a lot of reversal of the Texas coastal current, and there's also a lot of fresh water coming in from the Mississippi Atchafalaya system. That's why you get this nose of low salinity here with the darker blue. But in the middle of the summertime, August, the water is hot and it is salty because the currents reverse in the summertime, driving a lot of salt water from the Mexican shelves up towards Louisiana, and that's what's driving that. So this kind of pins you on what the hydrography was doing, and it does show very stark differences between what's going on in August, when things were very hot and very salty, and when the Hurricane Harvey, post-Harvey survey was happening, where things were still fairly hot, but a lot more fresh water. So that's part of the story. From the buoy side, we were able to see, so this is atmospheric pressure from the buoys as it was observed on each one of the different buoys. The 4 buoys are color-coded on the bottom, so X, J, K, and V, where X is this location, so that's the black line above. So this is X here. That's really the closest to where the storm passed over. J and K are the 2 that were down here near Brownsville, offshore of Brownsville. And then the last is V, which is out by the Flower Garden Banks. And so a couple things to notice here, because these are data, these are the observations. They give you an idea of what the temporal and spatial scale of the hurricane was as it moved through this region. But I do highlight here this green line, which says, highlight here, arrow with buoy heroes, because you can see the green line starts right there where that vertical arrow ends. And that's because we had a buoy team at the time in the water deploying our buoys at this particular location. K, they got the buoy into the water, started collecting data. They start going home. You can see it's within 24 hours of the storm passing by. They start going home. But of course, it's oceanography and things often go awry when you're in the ocean doing oceanographic work. The screws on the boat ended. They stopped working. So the boat really had to about 50 miles from here, turn the bow of the ship into the wind, into the seas, and they rode out the rest of the storm for about 2.5 weeks, almost 3 weeks. So for me, buoy heroes, right? That's why I have buoy heroes there. The other thing you can see on this is that there's a second low that happens several days later, and that's when the storm came back out into the coastal ocean. You can see that the atmospheric pressure in the coastal ocean then also went lower. However, not nearly as low as the approaching storm because the storm is already starting to dissipate at that time. Go. Oh, this picture is taken by one of our technicians, Adam, on the back deck of the boat, the Brooks McCall, about 24 hours into them sitting out, weathering the storm. And the story that Adam tells me is that this was the first time that he was able to stand up on the boat about 24 hours later. Puts that in perspective. So this is showing the buoy winds that were being collected in real time as the storm was approaching and then passed. I have two vertical lines on this showing when the first landfall and when the second landfall happened. This is shown in oceanographic representation. So this is showing the north, south, east, west components of the winds as the direction of which the winds are blowing towards, right? So this is the oceanographic representation. So these vectors here, these stick plots, show the direction that the winds are going. And what you can see here is that as the storm is passing by, you can see that the winds that were being measured really are reflecting on how the storm is passing by. We also have the coastal currents simultaneously with these winds, and this is set up such that the lower graph is buoy J, which is closest to Mexico, and buoy R, which is in actually Louisiana water, just off of coastal Louisiana. So it tends to go from this is at the top. It's more to the north and to the east, and as you go down in the graph, it's more to the south and to the west near Mexico. But the currents here have been rotated so that if the vector is pointing straight up, that means the currents are going towards up coast direction, which is a long shelf towards Louisiana. If they're pointing down, then they're going down coast towards Mexican waters. So this kind of shows the phasing of all those different currents as one transits along the coastal Texas coastal line. You can see here, though, as the storm approaches, how the winds had changed and how they reversed the currents. And that's coincident with when the storm makes either the first or the second landfall. Also, what's particularly important about this is that there is a fairly strong, persistent down coast. So from Louisiana towards Mexico during this week, the second week of September, which is what's driving a lot of where the freshwater effluent is now going down towards the Mexican shelves, which is what we then capitalized on in our cruise. So let's go here. This is just an animation showing just the different currents and also superimpose some of the winds from the NDBC buoys that's in red here as the storm makes landfall. Goes in near Victoria, Texas, spins, and then comes back out along coastal Texas. into the coastal water near buoy W, and then up the coast towards B, and then up even further towards R, and then in near Cameron. So this is just showing kind of the phasing and the inertial response and the of the winds and of the currents during the storm. So the phasing of salinity is really important. So it's where is the fresh water going? And so the upper graphic is showing where the north buoys are. And again, these are buoys B, R, F, and V. And buoy B is the one that's off of Galveston. Buoy R is the one that's Louisiana. Buoy F is just 30 miles offshore. And buoy V, Victor, is the one that's near Flower Garden Banks. Start with Victor. You can see that there's almost no signature of any fresh water going to the Flower Garden Banks, as by this blue line here. Never gets quite fresh. R is the first place where you start to see some movement. However, this first movement is done because the coastal current coming from the Louisiana shelves. It's really this large dip in the red graphic there, which is second, which is after the first landfall. So the first indication that there's the storm happening is really at buoy B. This is off of Galveston. Next is buoy R, then offshore at buoy F, and then and this is all within several days of each other. Never quite gets out to buoy V, and then in the southern buoys you see a different phasing. So this is X, D, K, and J, and D being off of Corpus Christi, or being the most north and east. You can see that the salinities start coming down there first, followed by J, which is the next southernmost one, and then offshore at buoy K. So these two graphics say that the response, the salinity response of the shelf started immediately after the first landfall. It's happened first up by Galveston. It started going down coast, and it took about a week for it to get to buoys D, J, and K down near South Padre off the southern Texas coast. The next graphic shows, so if I was to take all the data and I was to then do an optimal interpolation of all the CTD data, including the shipboard data for the September cruise, which was around September 20th of 2017, this is what the surface map looks like. And so blue here, where did I get red from? Blue here is the low salinity, and the yellowish colors here are the high salinity. And this is showing that that in September, after the storm, that it is the freshest water is pinned against the coast. That's consistent with what we just saw from the Tabs buoys. We also have here, as a comparison, the August 2017, so a month before and about a week before the storm made landing. This is showing very high salinities, so in 35s, 36 salinities, and throughout the region. So looking at this, you get a very good idea that there was very different hydrographic surface conditions along the Texas coast. I have one more on this graph. So this is a picture that I took on the boat. This was on the Point Sur vessel when we were doing the September cruise. This showed a line which was about 10 miles unbroken, showing a lot of unknown substance in the water. The boat, even though this picture looks like the boat is right on top, we tried to stay out, keeping any of this stuff from coming onto the boat and or coming into the boat. In fact, we had chemists on board that just refused to take samples on this. We still don't know what that junk was that was in coastal water. There, the arrow points to where that was, so it was close to a salinity front. We did make reports back to the General Land Office and other decision makers to send overflights. And my knowledge is that they confirmed that this feature was there. However, I do not have any information about what exactly this is, except that it's probably stuff that came out of people's yards and houses and roads post-storm. So we were able to, in order to do some freshwater balances here, we were able to do this gas Markov optimal interpolation. So the long history with this, some of the graphics or some of the references here show how to do that. I was also able to do this three-dimensionally, so this graphic is showing how to do that. Then in order to get the freshwater volume estimates, we used a good friend, Larry Atkinson's equation from 1981, so which allows for freshwater volume estimates by differences in the different fields using subtraction, using that formula there. And so when I talk about the amount of fresh water, it's using that equation here. So let's talk about that. So here we are. So this is so just a graphic that was in the Washington Post. So this is at the time contemporaneous with the storm, showing about what that many gallons. In this graphic, it has 33 trillion gallons. To put that in perspective, on this graphic, this is 3.1 miles. That's not what the final number is. So my number in the beginning of this talk is really what the satellites say what the total rainfall that fell is. But however, this gives you kind of a perspective within the context of downtown Houston, how much rain actually fell. The other thing to put in perspective here is that the Mississippi River outflow is about it's the largest river in the hemisphere. It's about 10,000 cubic meters per second. Say that again. 10,000 cubic meters per second is what comes out of the Mississippi River. That volume that's there, that's depicted here, this 3.1 mile cube, is equivalent to about 36 unbroken days of Mississippi River coming out Southwest Pass, which is the main stem of the Mississippi River, impinging onto the shelf. So none of the other rivers in the northern Gulf of Mexico even come close to this. I have some numbers on that later in the talk. So, but that puts it in perspective. 36, so more than a month of Mississippi River is what's accounting for that. That's how much rain there was. Because I have the CTD data and I was able to do the optimal interpolation three-dimensionally, this graphic here, which is the middle graphic, shows where the fresh water was as a function of depth, and this is by depth, right? So this is saying that most of that fresh water was in the upper 20 meters. If you take that graph that's in the middle here, and then you do the integration from the bottom or from the deeper parts towards, so just accumulate the fresh water as you go from deep to shallow, that gets you this graphic over here, which says, in the end, our graphic, our data from the cruise accounts for about 67 cubic kilometers of fresh water that would need to have been injected into the system between the August cruise and the September cruise. So that 67 is important. It's the number that we come up as the measurement for how much fresh water is out. Next slide. So if that was kind of by depth, this is kind of by, so plan view by location, by latitude and longitude of where that fresh water is. The lighter colors here are fresher. The darker colors here are saltier. And this is saying that between the September and the August cruise, the fresh water accumulated in where it's light here. And so you can see where the light colors are, it became fresher. And offshore, closer to the flower gardens, there was some slight saltier water that accumulated out there. If we move to a full accounting, I started at the beginning that 162 cubic kilometers is what fell based on the satellite precipitation measurements. We can divide that up into 118 that was on land and 44 that was on the ocean side. If we go, we take that, break that down a little bit further. So we move up to that diagram. We can start putting in numbers for how much was lost to evaporation and transpiration. Fortunately, the evaporative side that is on the land side, there's an estimate for that. It came out to be 28. On the ocean side, just using standard 1 millimeter per day per square meter, comes up with about 23 from that. it's better than that because it turns out that there's a paper that was published in 2019 that came out tracking the weight of Hurricane Harvey's stormwater using GPS reference data. So as it rained, that depressed reference stations and moved them. As the water then moved, it moved into groundwater. It moved into it evaporated. It got held up in embayments and dams. All that's trackable, and these numbers here, the ones in with the asterisk, are straight from the paper. So these are numbers that I didn't calculate; these are published. So it says that of the 118 that was on land, 12 moved into groundwater, 28 was evaporated, 26 was captured in embayments, and then that left a total of 52 cubic kilometers to then have run offshore through people's backyards and through the bayous along Texas. And so if you have the 21 that's precipitated directly and didn't evaporate, and 52 that then ran from the surface runoff from land to the ocean, that equals then 73. And what I just told you on the previous slide is that I measured 67. So I've done the error analysis on that number, and it's with so I have about a 5% error on that. So I think that number is a pretty good and robust number. So it says that we captured about 92% of what was expected to be on the shelf based on these numbers, given published estimates of what satellite precipitation is and what the reference data said should be accounted for as captured or evaporated on land. So going to here again, so this says again, so 73 kilometers, we measure 67. But if you go back into the USGS record, only 1 cubic kilometer of that was actually gauged, which meant that so 52 was predicted to come out, but only 1 kilometer was cubic kilometer was actually gauged. So this raises a huge challenge because a lot of the numerical models use the USGS gauging stations, but this is clearly showing that a lot of the data or a lot of the volume that went from land to the ocean was unaccounted for. So and so the numerical model, in order to do the prediction, should like where did the fresh water go, in order to be accurate, should adjust a bit for that. We do have our own model of this on the Texas coast. So this is Rob Hetland's model, which is now run by Yun Liu for the Texas General Land Office. But this particular animation is showing the storm, but this is also again only showing the gauge station, because the numerical model that's driving this is only uses the gauges. You'll see the storm approach here. You'll see it's undeniable right there. As soon as that storm makes landfall, you can see that there's fresh water coming out. You can see that it starts to move down coast towards Mexico. But also remember that it's only accounting for just 1 or 2% of what actually is coming out of those gauged locations. So there's actually a lot more fresh water, a lot more blue than what you're seeing in this particular model here. So the conclusion of this part of the talk is that the TABS network, so the buoy network, and research cruises provided real-time observations of the ocean before, during, and after Harvey, and that the network tracked the movement and distribution of the freshwater along the Texas coast, and that the plume predominantly moved towards Mexico. The plume did not move offshore. I have more information that I don't have time for to verify that too. But the 67 cubic kilometers of freshwater on the shelf accounts for about 41% of the total rainfall on both land and sea for this particular storm. I have to say, the study is not possible without a high-resolution precipitation satellite. That's the GPM that was out there. Also, an existing observing network, the TABS buoy system in place, was critical for having the data in order to understand how this storm impacted the coastal environment. Also, a terrestrial GPF reference system, and people thinking about it as the elastic response of the Earth as the Earth rebounds to all that weight of the fresh water. So this also emphasizes the importance of this sustained real-time in situ network, being adaptive, getting out there when you can, getting that rapid when we did, and also being lucky. It's good to be good. And it's really important to be lucky too. If we didn't have this cruise before the storm made landfall, we couldn't do this analysis. Okay, full stop. Good. So I have enough time to give you what I have for the next part of my talk. So full stop. The mini adaptive sampling test run experiment of 2024. This is completely different. It's in the Yucatan channel. This is part of the UGO's Understanding Gulf Ocean Systems project funded by, or the program funded by the National Academy. 2016, the Gulf Research Program Advisory Board was put together. 2018, the consensus study report was commissioned and released. That's that book that's shown to the right here. I was on that particular consensus report with a lot of other Gulf scientists. And to date, there's been 3 rounds of funding totaling about $40 million as part of this UGO system. The goal of the project in general is to advance understanding of the loop current and the loop current dynamics, to improve forecasting of the loop current and improve its predictive skill, and also to reduce risk to those working in the offshore energy sector. So we have a graphic, and that graphic looks like, come on, like this. So this is our roadmap. And for this roadmap, the red arrow here points to the green box, which is the mini adaptive sampling test run, which is what I'm going to talk about. The thing about this roadmap is that the yellow box on the left says that that engagement begins with stakeholders and understanding what the needs of the end users and stakeholders are. That feeds into the box that has all the different numerical and observational activities that then arrow down to this transition to operations pathway, because in the end, we want these outcomes to be usable by the community, right? So the finish line for us here is transition to operations, and that graphic to the right emphasizes the importance of going from research to development to demonstration to deployment of operational systems. So the MASTR experiment. So had multiple elements. There's many elements as part of this. The red font here is showing our industry partners on this. We deployed a series of gliders from multiple operators, including the Mexicans at CCPO, and they're based in Ensenada. Rutgers, so that's Scott Glenn, and then Texas A&M, that's us with Gerg. We also had University of Miami as part of this, deploying an Apex float. There was also drifters that the Woods Hole Group so Woods Hole Group is who owns Horizon Marine now. For those that know a little bit of the history of the industry involvement with loop current prediction. There's also the high frequency radar that's at what I showed before, which is a partnership between Texas A&M, Rutgers, and UNAM. And then we had Fugro as a partner, an industry partner flying overflights. And there's also Amy Bauer at Woods Hole that put in about 3 dozen Argo drifters. We also have numerical operational models. This includes the Navy model GOFS, the European Union model Copernicus or CMEMS, and then RTOFS, the NOAA global model. We also had the TOPS DA, data assimilation model, that is run for industry. All this couldn't have been done without involvement of the U.S. State Department and the departments, the international departments, the embassies with Cuba and with Mexico. It took about 2 years of phone calls and emails almost every day to get all the necessary permissions and you'll see why in a second. The MASTR team, so it takes a village, and so there was more than 60 researchers on this project. I was the chief scientist along with many others, 16 institutions, 3 different countries. We had the Regional Association of GQs also involved, the National Academy. You can see, I'm sure some of our folks on the call probably know many people that were on here. And I would just have to say, this is one of the most rewarding projects that I've ever been involved in the 30 years that I've been doing this type of work. Extremely collegial, very committed group working to common goal. So what did we do? This is just summary. We had 4 gliders. In the end, we had almost 300 days of glider work. What that upper left shows you is where the gliders were, where the trajectories took them. Notice that we got into the multiple times into the Cuban EEZ. That's the first time that's ever happened. It went from middle January all the way into May of 2024. Of course, the ship that was the little boat that we used to deploy the gliders is called the Black Pearl. Of course, it was. What else would it be called if not the Black Pearl? That have to be called the Black Pearl. And we covered, if you add up all those trajectories, so all the pathways there, we covered about 6,600 total kilometers, which is about the radius of the Earth. So before this experiment, not much data there. And after this experiment, we got almost 4,000 TS profiles in this region to 1,000 meters total water depth and covering about the radius of the Earth. So a lot of data being collected, and some of it for the first time, especially in Cuban EEZ water. Every time that the glider crossed into the Cuban EEZ, I had to write an email to the Cuban military stating that there was U.S. assets or Mexican assets crossing into their EEZ in these locations. All the data was done in real time. It was all being administrated by GQs, the Gulf of Mexico Coastal Ocean Observing System, so the Regional Association for the Gulf of Mexico, and it was all the data were free and accessible to anybody, including the Cubans that wanted it. So this is just showing again the locations here. One thing that we did discover as part of this research is that Banco Aerosmith is a real bathymetric feature that comes within 20 meters, less than 20 meters within the surface, and it has profound implications for the dynamics in this location, which a lot of the global models do not resolve. You have to go to one, I think Tal Ezra's on this call here. You have to go to 1 kilometer in order to resolve this bank. And so a lot of the models that I'll show you do not resolve. And so one of the things that we did learn with this is you really do have to go to these very high resolution models. We also had overflights, and this is showing where the airplane went. And so we tried to limit that to the overflights of the airplane to the location where the radar was. We also, so what you're going to see next is an animation. This animation shows the trajectories of the gliders as they transit around, and it's a time lapse of that. There is a soundtrack. I'll try to speak over the soundtrack. If it's too loud, let me know. Try to reduce that. But what it's going to show you is the radar footprint that's going to come in green. That's going to be up there in the Yucatan Channel. The gliders are down in triangles. The arrow associated with the glider is going to be the depth average current. So when the glider goes up and down 1,000 meters, we can back out, we can estimate what the depth average current is along that. And you can watch how the depth average current aligns very nicely with what the HF radar is showing. In this as well, you'll be able to see Argo floats come in. There will be circles as they come in and go. With this, you'll also be able to see drifters, the surface drifters as they were deployed. And without much ado, and I just have to say, just remember this: there was your life before you saw this animation, and then there's every moment of your life following this animation. So just saying, worth the price of admission. So here we go. So you should be hearing the Bumblebee theme. This is a public domain theme. And you can see the two gliders going through here. You can see the hourly radar in green. You can see that we just added 2 more gliders, so now there's 4 gliders in. The cyan color here is the NBDC buoy that's paid for by NOAA. And you can see that this dark purple is where there was drifter. You can see the red come and go, and that's where the Rocus overflights are coming in and out. You can see that black line there is where the 1.5 knot current is. You can see also the Rocus overflights coming in. You can see here as one glider gets then recovered, and that particular glider does not get put out again. But here we have the first Cuban transect. This is of the Rutgers glider. That was the blue triangle. So as that crossed into Cuban water and then crossed back out into back into the Mexican, the EEZ, we were writing emails back and forth. You can see Stommel, which is our glider, Texas A&M. You can see where the SG-652, that's the Cessna glider, is. You can see that Stommel is about to cross in, so we got our glider in as well. It was in the Cuban EEZ. It starts making the transect across. We're trying to get down into the Caribbean water that's entering into the Gulf of Mexico. Provides really good boundary condition. I'll say something about that in a second. As this progresses, now we're into the middle of April. The experiment's starting to wind down as the gliders are starting to get recovered. You can see where the Stommel is. It's about to be recovered here now. That's our glider. The last glider in the water is the Sea glider, the Mexican glider. That's the last one in the water. You can see the strong current there. You can see the proximity to the Arrowsmith Bank in the western part, and that is the end of that animation. So I don't know where you are, but if you would like to applaud, go right ahead, because that, to me, that group that was piloting those gliders were just amazing to me. They really, and some of them, I think Sakib is on the call too. One of the Texas A&M pilots on the call. Oh, that's not on the show. Cool. Yeah. One of the things that we came up with, and this is based on what the MIT group provided to us. So this is Pierre Lermersu, was a product that was called reachability. And this became a huge, very big aspect of what was going on in terms of what do the stakeholders and the end users need for this location. This is a very challenging environment. The gliders can only do 23 centimeters per second forward speed. The current, this is one of the biggest currents on the planet. This current can approach 5 knots or 2.5 meters per second. So flying a glider that can only go 23 centimeters per second in a current that's doing 250 centimeters per second became a very big challenge. And it became something that that we were asking for help. And so the MCs group at MIT were doing some work with some machine learning, and they started coming, this really grew organically. They started coming to our meetings, asking us, how can they help us? After a couple of weeks of just listening, then there was a couple weeks of asking questions, they started to put this product together, which is called reachability. Now, these papers are being published right now. There's a couple that came out in MTS Oceans 24 just in September. But this was given the numerical, and this particular numerical model output is from the MIT model, the ensemble version of the MIT model. Says, given all the flight characteristics of the gliders, and knowing what the environmental conditions are, can I get a glider with these flight characteristics to a certain spot in 12 hours, in 24 hours, in 36 hours, 48. And so each concentric ring that you're seeing here is 12 hours. So what this is saying is, if you want to get your glider to a certain location, and since there's about 3 days worth of concentric rings here, this is saying that in the white area here, I can't get a glider there in 3 days. I can't get it there because the gliders cannot reach that location. In fact, with this MIT ensemble model, The white here is showing where the ensemble uncertainty is the greatest. So what this is saying is, if I want to get my glider to a place that's very uncertain here, I can't get there in 3 days. However, if I want to get down into, if I want to buck that current and get down into the Caribbean Sea back as the glider starts here, I can make it there in 12, 24, or 36 hours if I have the right trajectory. So this became a very, very, that's two varies, useful products that the gliders pilots and the operational team started using every day, every 12 hours. They were making decisions based on this new forecast. The other thing to say about this, I'm going to skip this one and this one. I want to get here. Come on, come on, come on. No, go here. Right here. Before we did the experiment, there was no glider data. So vertical, there was no glider vertical data that was being assimilated into any of these numerical models. RTOFs, GOFs, CMEMs were not assimilating any data. And the issue becomes, and what you can see here is the glider data is shown here in blue. But the models here are shown, they're color coded with these RTOFs for red, this grayish color blue for the Navy model, and CMEMs in purple. You can see RTOFs is doing a not so great job for the subsurface salinity maximum, which is the subtropical underwater coming in from the Caribbean Sea. However, once the glider data started getting assimilated, that changed. So this is showing after, so this is about a month later, so this is the end of February, the previous one was the middle of January, that once the data started getting assimilated, that all these models, these operational models that we had access to, because of all the data being put out on the GTS, right? All the glider data is going out in real time to the GTS, the Global Telecommunications System. It all becomes available and it all becomes accessible. So really does show very importantly that use of subsurface data and getting it assimilated into the model makes the model better. So I think this is, I think it's, yeah, these, the rest here, so I'm at the end. So the rest here is just essentially the bottom line. There's lots of unexpected every time you do an experiment. I've been told this my entire professional life. You do an observation, you learn something new every time. That's essentially what this is saying. There's a lot of people that were on the Harve team. I already showed who was on the MASTR team. I do want to say, if you're interested in the color maps that I use in this talk, we use CM Ocean, that's Kristen Thing. They're available in many different platforms, including Python and MATLAB. If you like the color maps, True Colors of Oceanography, you can use them here. And then my last slide here is, this is our mantra: collect data, not dust. So we like to say that if we have an instrument in the back lab that's collecting dust, it should be out collecting data. It's not living up to its fullest potential. And this graphic here is just showing one of our buoys that's in the Caribbean Sea as part of the SETI sperm whale language study that's ongoing right now. Anyway, that's all I have.